way. At a point A comma B, we want to know what is the magnetic field. So it is mu naught by 4 pi I by D sine theta 1 plus sine theta 2. So this will work out to be, this is B, this is A. So because of this wire, it will become mu naught I by 4 pi B sine theta 1. This is theta 1. So that will become A by root over of A square plus B square plus 1. Now this magnetic field will be inside the plane of paper. So it will become minus, so K cap, plus mu naught I by 4 pi A B by root over of A square plus B square plus 1. Again it will also be minus K cap. So the magnetic field at point A comma B is equal to this much. Please make some notes. Yeah. Then if I have to check any messages from you guys, 4 messages, I hope they are not just groom. So can you zoom in little please? Okay, class 12 results came. Yeah, I have not seen, I have just heard. So from Madurai you have got 484. So other schools I'm yet to see. Basically I'm having class now. After my class I'll be seeing. Yeah, I can mark theta 1, theta 2, no problem. So you wanted me to zoom in a little. Here it is zoomed. So this is theta 1 and this goes this way because it is infinity. So this will become theta 2. Here it is theta 1 and then here it will tend to 90 degrees. Okay. So if that is understood, then good. That is Bayes-Savart law. So let me just see any other messages. Yeah, anything else that you want? So this is what is Bayes-Savart law. We can keep going on and on and on. So in the last class I explained to you that if there is a clockwise, this is an anti-clockwise current. If there is a anti-clockwise current, you get this. This is a north pole. Now if there is a south pole, if there is a clockwise current, so you get a south pole. So anti-clockwise is north pole, clockwise is south pole. Then I also explained to you integral B dot dA is equal to 0. This is Gauss law in magnetism. Okay, this is Gauss law in magnetism. Yeah. So good, if you understand this, then okay, let's move on. Next is Ampere's law. Also referred to as Ampere's circuital law. Ampere's circuital law. Suppose there is a wire which is carrying some current, and suppose this is an Amperean loop. Then integral B dot dl is equal to mu naught I. Integral, this is a line integral. Line integral. The circle here implies that it should be a closed figure, where I is the current passing through the wire, through the loop, Amperean loop. Integral B dot dl is equal to mu naught I. It's a line integral. Yeah, closed figure. It should be a closed figure. I is the current passing through the Amperean loop. This is Ampere's circuital law. The line integral of B over a closed loop is directly proportional to the current passing through it. The line integral of B over a closed loop is directly proportional to the current passing through it. If this appears, it appears as a question. Okay. Sir, this seems similar to Gauss law in electrostatics. No, it's similar to Gauss law, but Gauss law is over a closed surface, while this is over a line. So don't misunderstand. Gauss law in magnetism, I have already explained to you. Every week there will be test. Okay. Yeah. So if you guys understand that, here we'll move on. So now suppose there is an infinitely long current carrying wire, and you want to know what is the magnetic field here. I draw an Amperean loop. Yeah, I draw an Amperean loop around it. If I draw an Amperean loop around it, integral B dot dl is equal to mu naught into I. So B is constant because it's at a constant radius, it's constant. So B integral dl is equal to mu naught into I. So B is equal to mu naught into I divided by 2 pi r. The length of this line here is 2 pi r. So the magnetic field near a wire, an infinitely long wire, is equal to mu naught I by 2r. So this is how easy it is for us to calculate or determine. B is equal to mu naught I by 2r. Okay, the same thing we have determined. This is what is there in our syllabus. By using Biot-Savart law to determine this is not in our syllabus. So this also comes usually as a 2-mark question. Okay, so I hope this is understood. Portions for the coming week test. Portions for the coming week test is moving charge, voltmeter, all the way up to voltmeter. Always test will be there, all Sundays, all Saturdays, all weekends test will be there. The portions I have just now explained to you. Up to voltmeter, whole of moving charges. Okay, next. Yeah, this is a solenoid. It is a helical coil of wire. Yeah, it is a helical coil of wire. This is a solenoid. It is a helical coil of wire. Now, if a current is passed through it, a very strong magnet, it gets converted, or it becomes a very strong magnet. A strong magnetic field is induced. A very strong magnetic field is induced. Okay, so we will discuss how this happens. See, here is your loop. So we already discussed, if you have a loop of this kind, that there will be a magnetic field this way, in a circular way, there will be a magnetic field around it, right? So there will be a magnetic field here. Now suppose I have another loop here, and the current is flowing in the same direction. Now here also there will be one magnetic field. This magnetic field will also be in the same direction. Yeah. Now suppose I bring them together. Do you see that at the middle there will be a superimposition of lot of magnetic fields? There will be a superimposition of lot of magnetic fields. Yeah, because of this superimposition, a strong magnetic field develops inside the magnet. Okay, a strong magnetic field develops inside. Here also there will be a good magnetic field. So they are all in the same direction. Because these magnetic fields are all in the same direction, what happens is that there is a superimposition of lot of fields, and because of that a strong magnetic field develops. Yeah, are we able to understand? So this is what, yeah, this we'll take it up subsequently. Yeah, so Senthil, I will discuss it, don't worry. It'll yeah, so let's work on this. Yeah, so this is basically a solenoid. Typically if you go to the market you will get solenoids which will have 10,000 or 50,000 turns per meter, or even more than that. When I am drawing them with some distance. In reality they will be like this, superimposing, there will be lots of turns. Here I am explaining 50,000 turns per meter, 10,000 turns per meter, 1 lakh ton per meter. Okay, so a solenoid has a length, then an area, and turns per meter, number of turns per meter. So when you go to the market, you tell that I need a solenoid which has 50,000 turns per unit length. 50,000 turns per unit length, and you get this. So this is how it works out. Okay, so this is turns per unit length. Yeah, now we want to determine, sorry, now next one I'll do. Now we want to determine what is the magnetic field. I said there is a strong magnetic field. I want to determine what is the magnetic field. What is the magnetic field inside the solenoid? Okay, for that I will use Ampere's law, and then I will try to work it out. So here is a solenoid. Okay, now if I want to know what is the magnetic field, so here I am drawing an Amperean loop. I have drawn an Amperean loop, part of it which goes through the magnet, through the solenoid, and a part of it comes outside. I have already explained to you that the magnetic field inside the solenoid is in this direction. Yeah, because the overlapping happens along this, so there is a magnetic field in this direction. So I am looking at that magnetic field. Okay, so A, B, C, D. So integral A to A to A, B dot dl is equal to mu naught into I. Because it is a closed loop, I can break it into A to B, B dot dl, plus B to C, B dot dl, plus C to D, B dot dl, plus D to A, B dot dl. So from A, I have come back to A. Yeah. Now this integral is equal to 0. Why? Because the magnetic field is in this direction, the dl vector is perpendicular. So This is 0 because dl is perpendicular to B. Yeah, same logic, even this is equal to 0 because dl is perpendicular to B. Now this is equal to 0 because it is assumed that there is no magnetic field outside the solenoid. It is an assumption. It is an assumption that B is 0 outside. So if B is 0 outside, this B dot dl also becomes equal to 0. Yeah. So the magnetic field inside the solenoid, if I am applying Ampere's loop, is simply equal to, is simply equal to B dot dl. Now in this, B is B, dl is this length. So I'll say this is equal to mu naught I. So BdL is B into dl is equal to mu naught. What is I? Now you see there are so many turns here and each turn is carrying a current. So how many turns are there? Turns per unit length into dl. So that many turns are there and each is carrying a current I. So this I net is equal to N dl into I. So the dl here get cancelled and you get B is equal to mu naught into N into I. So the magnetic field inside the solenoid is mu naught into N into I. Can you work this out? Okay. Yeah. So if this is understood, let me just come back. I net is equal to, no, N is the number of turns per unit length into dl. Only that will give you the total number of turns. So in this, how many turns are there? N is the number of turns per unit length. dl is the length. So the total number of turns is N dl. N dl each carrying a current I. So integral this end to this end is B dot dl. So that B dot dl is equal to mu naught into I. I will be number of turns into dl into I per each turn. So that is equal to mu naught N dl into I. So the dl gets cancelled and I will get B is equal to mu naught N into I. Now that N that we are talking of could be 10,000, 20,000, 50,000, 1 lakh, even 2 lakhs, even 3 lakhs, depending on what kind of a solenoid you have. So this is the magnetic field inside the solenoid. Okay, we should try to do this 2-3 times. Only when you try to do this 2-3 times, answers will come. So here it looks like this. So current is going this way. So I try to find out what is the magnetic field inside. So I've drawn an Amperean loop this way. So this is A, this is B, this is C, and this is D. So if I apply Ampere's law, integral A to A, B dot dl is equal to mu naught into I. Now this I can break it from A to B, B dot dl plus integral B to C, B dot dl plus integral C to D, B dot dl plus integral D to A, B dot dl. Okay. Now here the dot product is 0. Why? Because current direction and magnetic field direction are perpendicular. So this is equal to 0. Same logic for this. So this is also equal to 0. Outside it is assumed that the magnetic field is 0. So because it is 0, this is also 0. So all that we are left with, integral B to C, B dot dl is equal to mu naught into I. So B is same, B dl is equal to mu naught I. I is the total number of turns in that zone, in this much. So N dl into I. So the dl here gets cancelled, and I get B is equal to mu naught N I. So B is equal to mu naught into N into I. Okay, so this is how you find out. Okay, this is Ampere's law. It's a very important question. Yeah, it's a very important question where we are applying Ampere's law. So the first application we saw was a straight wire. The second application we saw is a solenoid. A solenoid is a helical coil of wire. Helical like a spring. Okay. No, N is number of turns per unit length. Okay. Yeah, so if I can get some response, I will move ahead. Do you guys understand what we are saying? You want more time? I don't know, you guys don't ask questions, you don't speak, so I don't know whether you guys are sleeping or whether I'm teaching fine and you're understanding everything. So I don't know. Okay. Okay, so if you understood this, then let us move on. So if you understood this, then let us move on. So this is a solenoid. This is a solenoid. Okay, it was straight. It had some length L. Suppose I convert, make it round like this. into a circle. Now what will happen? Now do you understand that at this point the magnetic field B is equal to 0 because it is outside the solenoid? Yeah, but if you see here, it is equal to B is equal to, for this it was mu naught into N into I. The moment you took it of some L into N and you moved it into a circle, now the circle has 2 pi r. So do you understand that the new number of turns per unit length is L into N by 2 pi r, or capital N by 2 pi r, where capital N is the total number of turns. Capital N is the total number of turns, that is, which is equal to L into N. So yeah, now such a magnet is referred to as a toroid. The magnetic field inside the toroid is mu naught N. N is N divided by 2 pi r into I. So that is the magnetic field inside, between the between the coils of the toroid. Here at this point P, magnetic field is 0. At this point P also the magnetic field is 0. So the magnetic field outside the toroid is 0. Magnetic field outside the toroid is 0. Yeah, even at the center of the toroid, the geometrical center of the toroid also, it is 0. In between here the magnetic fields are very high. So that is equal to mu naught N by 2 pi r into I. Yeah, so that will give you the magnetic field there. Yes, if you can make some notes. Okay. So if you have done 2 pi r, 2 pi r is the, it is not small n, capital N for total number of turns. So you are taking a straight solenoid and you are bending it into a circle. So this L is becoming 2 pi r. So N divided by 2 pi r. So that will give you the number of turns per unit length. Basically a straight solenoid, is basically bent to form a circle. Yeah, a straight solenoid was bent to form a circle. So the number of turns per unit length will be changing. Yeah, okay. Anything else? Then why are we multiplying and dividing? Huh? Yeah. L is equal to 2 pi r, correct. But number of turns, we want to find out number of turns. So generally when you go to the market, you may say you give me 2 meters, you may also say give me 2 lakh tons. So if you're going to the market and buying 2 lakh tons and then you are putting it in a circle, we have 2 lakh divided by 2 pi r. Okay, so if you are not doing it, fine, no issues. Yeah. Okay, so if this is understood, very good. Then I have a cylindrical wire. and I'm passing a current through it. So when I'm passing a current through it, do you understand that I by pi r squared is equal to J, the current density. The current density. So now, if I draw an Amperean loop here, there is some current which is passing through it. So B into 2 pi r is equal to mu naught into current density I by pi r squared into pi small r squared. This pi gets cancelled. This r gets cancelled, and I will get B is equal to mu naught I by 2 pi r squared into r. What does it mean? It means that inside the wire also there is a magnetic field, and that magnetic field looks like this. So till I go to the surface of the conductor, the magnetic field will be proportional to r. The slope of this is mu naught I by 2 pi r squared. Now as I move away, B will be inversely proportional to r. Outside, B is equal to mu naught I by 2 pi r. So this is r, this is B. Initially it increases, this is capital R, then it decreases. I hope you remember having seen this kind of a diagram. Yeah, this is the fourth application of this, that is the magnetic field inside a current carrying wire. Magnetic field inside a current carrying wire. If you can make notes, we will move on. Okay. So if you understand this, we are talking about what is the magnetic field. So far, we have never looked at that. We have assumed that wire is a straight line. But wire is not actually a straight line, but it is a cylinder. Okay, if it's a cylinder, even inside the wire, there is a magnetic field. So we want to know how to get that magnetic field. So suppose a current, uniform current is I, then the current density is I by R squared. Now the question is, what is the magnetic field at a distance small r from it? So for that, I will use Ampere's law. Integral B dot dl is equal to mu naught into I. What is the I? I is the current which is passing through that loop. So that current will be mu naught into density into that area. Now this is equal to B into this circumference. Circumference is 2 pi r. So here pi gets cancelled, r gets cancelled, and I will get B is equal to mu naught IR by 2 pi r capital R squared. This is a constant, this is a variable. So as you move from the center, the magnetic field keeps increasing. Now outside the wire, if I ask you what is the magnetic field, what will you say? It is mu naught I by 2 pi r. It is inversely proportional. So it goes this way. So now this is the radius and this is the magnetic field, this much. Then I can ask you what is the slope. So the slope is this much, mu naught I by 2 pi r squared. This is the slope. Okay. Okay, so please think, please make some notes. Once you do a little, then I will move on and then we will move ahead. Slowly, 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 we are coming to an end. Okay, so if it is done, then we are, this is not the end of the chapter, we still have more time, more. Sir put here, but here we have j is equal to, okay, but we are multiplying it by capital R is the radius of the wire, small r is the variable radius. Once you go outside the wire, you have to take the entire current. Once you go outside the wire, what is the current inside this? That is the I. But what is the current inside this? That is not I. So the small r, as long as it is still r, we are getting it this way. After you go outside the wire, then it is always inversely proportional to r. Yes. Next week, I don't think we will be doing any classes. Next week, I just want to call each one of you one by one, and then I want to check out your notes. Look at your notes. Okay, so next week, Monday onwards, mostly we will not be having classes. I will be doing full online note checking. So what I will do is I will call you one by one. I will call you and I will ask you to show me all your notes. So please get prepared for it. Yeah, physics, chemistry, maths. I will check all 3 notes. Biology also. So please get prepared because I have to do it for each one of you. It will take little time. So I'm expecting that it will take 3-4 days. No telling me that I will show you later and later and all. So I'm not going to allow classes till you show me the notes. Yeah, biology also. Biology, bio ma'am will also be there, but I would like to check. Yeah, midterm marks are mostly corrected, so you should get them this week sometime. You will get them, except for a few papers where you have mailed it or you have sent it to me and then I have not made note of it. There are few papers. Other than that, the rest of you will get it. Once the other few papers also point out, we'll quickly correct it and give it back to you. So the midterm marks are all ready now. Okay, so we have corrected them and then they are all ready. Okay, so now if this is done, then we move on. Okay, So here is the next question. So theoretically we have done, there are a few more applications which I want to work with. Now, do you understand, suppose there is a wire here, it has a magnetic current going this way, that at this point B is equal to mu naught I by 2 pi d. This distance from here to here is d. Do you agree? We'll call this I1. Yeah. Now, suppose there is another wire here which is also carrying a current. Let's call this I2. Now, this is a current carrying conductor in a B, in an external magnetic field. Yeah, this is a current carrying conductor in an external magnetic field. So there will be a force acting on it, B into I2 into L. So can I say that this will experience a force which is equal to mu naught I1 I2 L by 2 pi d. What will be the direction of the force? Magnetic field will be into the plane. If I apply my right hand rule, the force will be in this direction. So if I call this wire 1, if I call this wire 2, this is the force on 2 because of 1. Now if you check on this wire also, there will be a force, and that is the force on 1 because of 2. Now do you see, it reinforces the fact that forces always exist in pairs, always exist in pairs. Do you see that action is equal to reaction? Because the force on this wire is also going to be that. We are more interested in force per unit length. So that is equal to mu naught I1 I2 by 2 pi d. So this is because I1 and I2 both are there, it will be the same on both the wires. So action is equal to reaction. And do you observe the third one, that action and reaction act on different bodies? Yeah, action and the reaction act on different bodies. There is one force on this one, there's another force on this one. Do you understand this? Can you make some notes? So do you understand that two parallel current carrying conductors attract each other? Yeah, two parallel current carrying conductors, two parallel current carrying conductors attract each other. Two parallel current carrying conductors attract each other. Yeah, so if they carry current in the same direction, they'll attract each other. If they carry currents in opposite directions, they will repel each other. Yeah, can you make some notes? Yeah, so if this is understood, sir, how will the magnetic field be inside the plane? Rick, hold the wire with your right hand. See how your fingers are going. Yeah, so it is inside the plane. On the computer, it is going inside. If you hold the wire with your right hand, the fingers are going inside. Only then you will be able to bring them to the other side. I here L is the length. If we were in school, we could at least say a lie that I have left my note at home. Yeah, true. Now the only thing that you can say is some friend of yours took it and is not giving it back, or there is full lockdown and I'm not able to get it back. But please don't use that excuse. Then I can call that friend and ask him to come. Okay. Anyway, don't worry. So okay. So I hope we are able to get it. Yeah. So if you are able to get it, good. If you are not able to get it, ask me. Okay. Now this gives us a very important formula or a definition. 1 ampere. 1 ampere is that current which on passing through two infinitely long wires separated separated by a distance of 1 meter produces a force per unit length of 2 into 10 power minus 7 newtons. So I said F by L is equal to mu naught by 2 pi I1 I2 by D. So now we are saying L is equal to 1, D is equal to 1, I1 is equal to I2 is equal to 1. What is value for mu naught? 4 pi into 10 power minus 7 SI units divided by 2 pi, cancel. So that is 2 into 10 power minus 7 newtons. So this gives me the definition of 1 ampere. So from now onwards, in any exam, if they ask you to define 1 ampere, we don't say when 1 coulomb passes through a given cross section in 1 second, we call it 1 ampere. No, this is the definition of 1 ampere. So if you go to the Geneva Weights and Measures Museum, they will show you what 1 ampere is. So 1 ampere is that current which on passing through two infinitely long wires separated by a distance of 1 meter produces a force per unit length of 2 into 10 power minus 7 newtons. Okay, so make notes. Okay. Yeah, okay. So good. I will show you the slides. I'm mostly done with what I want to teach today. This is not required for you. This is the one. This is the second one. Third one. Then this is the fourth one. Yeah, this is the next one. This is the next one. This is the next one. I don't know why I write so many slides. I can reduce them. This is the next one. This is the next one. Next one. Next. 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 This is the last one. Okay. So good. Thank you. So for questions, the theory is always, sir, which would you prefer, Halliday Resnick or H.C. Verma? For questions. For questions, I would do both. H.C. Verma is good. Do H.C. Verma, more than enough. Yeah, do H.C. Verma. Okay. Yeah. Okay. Bye. Bye. Yep. You're welcome. Thank you.